this is, I think, an area that really needs more people to work on, and hope I can tell you a little bit about the exciting things we are doing. So the topic is towards CFD-based design of the long-time behavior of chaotic aerodynamics. I'm going to talk about what is chaotic aerodynamic first, and why do we want to design the long-time behavior of these aerodynamics first. So for example, if you look at an airplane, right, this is a simulation done by ANSYS and Airbus, and the particular field focused on the part of the wing which the engine is mounted on. And you can see there is a lot of small scales in the flow field that looks chaotic and turbulent. And it doesn't just look chaotic and turbulent. There are features in the flow field that amazes me. For example, if you take a snapshot of the picture and you either run a simulation or run an experiment, flow visualization, from this point on, what do you think, I'll ask you, is the chances I'm going to see this flow field, the same snapshot again? 0. I will never see that again. Chaotic flow field means once you have a snapshot, the same snapshot is never going to appear again. There are new features, new things being generated, new structures generated all the time that are different. Statistically, it will look like it's stationary, but every snapshot is a new snapshot. It's almost generate things from nowhere. Also, this kind of flow field is extremely sensitive to small perturbations. If you change any small things in the flow field, and if you're able to compare the flow field with the change and without the change, the two flow fields will become very different after a small while. That is actually why, if you do experiments with a chaotic flow field, you can never repeat the same experiment again, right? Even if you tune everything to as equivalent as possible, you never see exactly the same movie you produce with two experiments. This is also why we can predict the weather. If you want to predict the weather 10 days from now, you just can't, because even small errors in our current knowledge of the state of the atmosphere right now is going to lead to very wrong predictions in 10 days. So chaotic fluid dynamics is in the atmosphere, on airplanes, also inside the engines. The whole combustion process is chaotic. It's designed to be chaotic so that you can mix the fuel and air in a small space. Now all of this chaos, especially on the airplane, begs the question. There are so much unpredictable, fundamentally unpredictable dynamics on the airplane. So why is flying actually so reliable and so predictable? So almost seems like deterministic. You would never expect the airplane to take off with half of the runway in one day, and another time on almost the same condition, it'll take the entire runway and doesn't take off, right? So what do you think makes the flight of an airplane predictable while there are so many chaotic dynamics in the airplane that is not predictable? The smaller scale?
Small in scale, yeah.
Okay, so small scale. Why is small scale makes the airplane predictable?
No, I meant the chaotic dynamics is small in scale when you compare it with the whole flow field. So
you're saying the chaotic flow field is small compared to the whole flow field?
maybe.
All right, maybe. But how about the engine? The whole combustor is almost operating as a chaotic system. That's the entire combustor. What makes the jet engine producing thrust in a predictable way?
So if the average still almost the same.
Average is a good word. Okay, so the average expressed scientifically is a word called ergodicity. Ergodicity means that, for example, for an airplane, if you think of the dynamics of an airplane takeoff, it happens over many seconds, right? And if you look at the time scale of the combustion or time scale of the chaotic dynamics over the wing, it's in milliseconds. So the dynamics of the entire aircraft depends on averaging these chaotic dynamics for much, much longer than the characteristic timescale of the chaotic dynamics itself. And this brings the concept of ergodicity. When you average the behavior of a chaotic system, of an ergodic chaotic system for a long time, then the time average, first of all, is the same for almost any initial condition. That means it doesn't care what initial condition starts with. The long-time behavior is going to be the same. It almost is like a steady-state system. And also, it's equivalent to average over a well-defined ensemble. That is also very important. And the long-time average, if you're into mathematics, is defined like that. All right, so Jeremy, I think you wrote down something very similar to this on the board 30 minutes ago. So look at what this is. U of t is the solution of a chaotic dynamical system. For example, the Navier-Stokes equation. J is a quantity of interest that is dependent on the solution. This can be the lift, the drag, the thrust, or some quantity you're interested in. This integral integrates that quantity over time. And an integral over time divided by the length of the integral is average over the time t. And then this is a limit. Take the length of the averaging to infinity. That's an infinite time average. It's also called the statistics in the jargon of turbulent flow and turbulent flow simulations. And these are the two people, Poincaré and Birkhoff. They are the pioneers of the theory of ergodicity. And although we still can't really prove mathematically that Navier-Stokes equation under any situation is actually ergodic, but we have a lot of numerical and experimental evidence that a lot of turbulent flow fields do behave ergodically. So this is the fundamental building frame we are going to be using in our study, because this really tells us what we are doing had some meaning, right? Otherwise, what are we doing numerical simulation for, right? Otherwise, when you perform numerical simulation, you know it's different from the actual physics. And we are confident we are actually predicting the statistics because of ergodicity. Because if you make a small perturbation, the result is going to be similar.